It's my great pleasure to welcome you on the third part of our tutorial called Openness in Radio Access Network Design in 6G, the ORAN concept. My name is Adrian Kliks and I am CTO at Remote Labs, and also I'm an associate professor at Poznań University of Technology, where I am concentrating on wireless communication networks. Now let me switch off my video camera to concentrate on technical parts of this tutorial. Okay, so as in the previous part, my colleague concentrated on OpenRAN concept and the OpenRAN architecture run intelligent controller. I will focus on xApp design. I will introduce how this xApp has been designed, focusing on the traffic steering use case. This is necessary to understand the virtual app, which is the fourth part of our tutorial. So, before going into the detail of the implementation of the selected use case, let me go briefly through different use cases which has been identified within the OpenRAN community, and also I will briefly discuss the deployments which have been also realized, and some implementations and real world. So maybe some first historical view. So originally, when OpenRAN Alliance proposed these use cases, these were split in two parts. There was phase one with some use cases identified, and also phase two with some other use cases left for further study and further implementation. And having this in mind, we as Remote Labs, we have concentrated on traffic steering, and we try to implement it on the Open Networking Foundation framework. But nowadays, these phases have been, there are no phases, simply. We have quite a broad set of use cases. You can see there are 19 of them. Some of them are left for further study, but in fact we can see that the variety of use cases is somewhat huge. So we can see some handover management for V2X communication. We have UAVs here. We have quality of experience optimization, traffic steering, of course, is there. We have massive MIMO, and many others. I will not go into the detail of each of these use cases. I will maybe concentrate on some specific examples of this ORAN-based use cases. So here we have the first use case selected, which is context-based dynamic handover management for V2X. As it is foreseen, V2X communication is one of the key application implementation in the context of future wireless communication networks. It is foreseen that this V2X communication will lead to improvement in overall road safety. It will improve road utilization efficiency, time saving, and so on and so on. However, there are some problems related to this, so we can foresee that for high-speed cases like in highways, there will be numerous handovers due to the nature of nowadays networks. So there are many cells, and the number of handovers will be simply, there will be many handovers. There will be also many handover anomalies which we like to avoid, so a short stay in one cell, the ping pong effect. And there's an observation that by using some past navigation radio statistics, one can customize handover in the V2X scenario, and the role of the xApp will be to tackle this particular problem. Okay, and the second use case that I would like to discuss is this quality of experience optimizations. So one can observe that there are many applications that consume much bandwidth. Also, these applications are quite latency sensitive. And the solutions we have nowadays, so that based on some semi-static quality of service frameworks, they cannot satisfy the diversified quality of experience requirements. Do some estimation and prediction are needed and may be helpful. And the concept here on this use case, and of course we can have in mind some xApp or RApp, in fact, then within this xApp, or the xApp should utilize all the benefits coming from the machine learning tools, where we can collect and process such data as traffic types, quality of experience measurements, some network reports, and many others. and to use these models, which could be quite generic, to support any specific quality of experience use case, which is very challenging and very interesting scenario. Okay, this is the second one, quality of experience. Previously, I discussed about this V2X. As you can see, there are many others. So the variety is really great here. So we have a great potential of improving of this network performance by adjusting the some specific xApps towards implementation and of these use cases. I would also suggest to have a look on this specific documents. There is a nice document, Open technical priority document, so that shows some priorities from the operator perspective. So this is the page where you can find it. And as it was written, the goal of this document is to provide a list of technical requirements, of course, from this perspective of Open RAN Alliance and all the parties involved here. There are two priority levels: P0, which is must-have, and P1, which is nice to have, and there are three priority types: anonymity, majority, and minority, which corresponds to these numbers of operators expressing this particular priority. I will not also go into detail, but for those who are interested, there are different sections of these documents focusing on, for example, CU/DU aspects, ORU general details, and so on and so on. And on the next slide, I am showing a very small fragment of this document, which exactly specify the priorities and the different priority levels and types expressed by different operators. It's very nice document, and I really encourage to go into detail of this particular one. That will show the view and will allow us to understand what is the vision expressed by the Openness members. Okay, as I mentioned before, we described use cases in general. Now let's go through some deployments. Here I concentrated on the last 2 years, so starting from February 2019, where we see the Rakuten implementation when we have 4G vRAN and virtual core by Cisco. So we have Cisco, Nokia, Altiostar involved here, so we can treat it as one of the first Open RAN deployments. Then there are some others, like we can see some Mavenir, Docomo, and Vodafone, and many other well-known companies involved in these deployments. I'm not promoting anyone here, of course. Here, maybe on the last one is most important from my perspective, as it works on exactly on the same framework as we did and we are doing in this tutorial. So when ONF, Open Network Foundation, and SD-RAN. So this is the Deutsche Telekom. With ONF, they demonstrate fully disaggregated Open RAN with OpenRig platform with, of course, Intel and Radices. If we go to the, if we look on the how these deployments corresponds to different parts of the world, we can see that there are many companies and many countries involved in this process of this global trend towards openness in RAN parts of the wireless network. Of course, I will not go into detail of the analysis of the specific deployment. I just selected 2 of them. First, the comparison of, how the network looks. From the traditional perspective. And one and other deployments. So as you can see here, there's a nice figure comparing this traditional approach versus Rakuten approach and Dish approach. So in the traditional one, we will have, let's say, the 5G network. We will have proprietary interfaces. We have MNO and detailed equipment, purpose-built hardware, and we have, of course, MNO centralized, localized on MNO servers. Then if we go to the 5G ORAN implementation, in the middle of this figure, we see that these interfaces could be turned into the open interfaces. So we have this open infrastructure. What is important here is that we go through virtualization. So this is fully virtualized cloud native 5G RAN and core implemented all on a COTS server, which is very important. So this edge part, regional part, and central part, these are implemented on the COTS server. But then the next step is to apply some hosting, as it was proposed by Dish Wireless. So we can see that the Amazon framework, Amazon infrastructure has been involved in this implementation. So which is also very innovative in the context of wireless communications. As I mentioned, from our perspective and implementation of this traffic steering on SD-RAN, here this Deutsche Telekom trial, called also Berlin trial, they involved this Micronos framework. Micronos I will talk about later. Micronos is the rig within SD-RAN. So here, as you can see, there are some ORUs which are controlled and associated with this rig, and there are in this figure there are two xApps deployed here. More could be added, and this is I am mentioning this because it is ongoing. Some new xApps will be included, and as I said, this is based on the ONF, and this is also subject of this tutorial. As you can see, there are some other big companies involved here, like Intel with their SmartJet Open, Radisys as well. We have Facebook and AirHop, just to mention all of the partners involved. Okay, so this will finalize the introductory part of this part 3 of this tutorial. Now let's have a detailed view of the specific use case, which is traffic steering use case. So if we think about the traffic steering, we can say that the key question is, as you can see on this figure, the key question is that how to associate in the best way the UEs to the base station. Of course, typically we are treating all the UEs in the same way, with some average values, with some statistics, and we are highly limited with the opportunities what we can do with the specific UE. But in fact, these UEs, they have different requirements. They have different types of traffic. So customization, in fact, is a need to have this UE-centric view. So the aim here is to allow operators to specify different objectives for traffic management. It can be done through some optimizing of the network performance, UE performance. We can achieve different goals, and this will be available through flexible configuration of the network through, for example, policies. Of course, for this specific use case, we can specify some required data that will be necessary before we start any modification of the network. So we could have, for example, this RSRP, RSRQ, CQI as the input to our function, and at the end we will have some association tables. We could improve again, for example, the handover, and we can improve some statistics. But the key question is that we would like to have UE-centric and policy-based flexible tool to allow us to associate users following some requirements specified by the mobile network operator. So if we try to project it on the Open RAN architecture, so this is shown this and the two following slides. So on the left side we see that the situation we have a heterogeneous network. We have cell A, cell B, so two different frequencies, two bands, and cell C, cell D, another two frequencies which can be used in the network, and we have two UEs, UE1, UEB. So now let's focus on the blue one. The question is how to associate this particular UE, either to associate it with the first G node B or maybe with the second. The question is important. The answer is not that straightforward, because it may have a voice connection with 5QI equal to 1. It may have MBB connection with 5QI equal to 9. There are different ways how it could be connected, either in the frequency 1, frequency 2, and or frequency 3, which are represented by cell A, B, and C. So the question is important, and the answer is not that straightforward. So this observation, as we can see on the right side, this observation will be used on the entry to our traffic steering xApps, and of course different operators may have different priorities, different policies how to deal with such specific users. So if we look on the right side, we have this non-real-time rig that will provide some policies to the near-time rig and this traffic steering xApp which will reside on it to steer the traffic in such a way that all the requirements specified within these policies will be fulfilled. And of course, these policies, if we follow the Open Run Alliance, these policies are specified in some JSON scheme. So there are different parts of this JSON file. Here we are just highlighting that these priorities, these policies may be applied to different domains, let's say, of the networks. It can be applied to the slice. It may be applied to some cell ID, some QoS ID. So the policies may specify different aspects, different parts of the network, and how to deal with some specific elements of the network, let's say it that way. On the right side, we are just concentrating, we're just showing the part which is important from the perspective of this tutorial. So we have this preference type, which express the preferences of the operator. So there are 4 elements: shall, prefer, avoid, and forbid, which express different attitudes, different expectation of the operators, how to deal with specific traffic. Once the policies are delivered to the new real-time rig and applied, at the end we have the results. We have this association table, which will be delivered through E2 interfaces to E2 node, and at the end it will be applied, changing the association. So all necessary procedures to change the association will be executed, but these instructions will be delivered to the E2 node. So this is the generic overview how the traffic steering xApp should operate. So now, okay, let's go to some detailed analysis. So this scenario, maybe have another look. So we have maybe another way. Before we implemented the whole traffic steering use case in the SD-RAN, we have made some initial tests to see if the algorithm itself works as we expect. And now in this part I will show you the concept behind the traffic steering, what we have done, sorry. And then in the next part we will show how this particular traffic steering xApps has been implemented and added in the SD-RAN. So for our local testing and evaluation of the performance, we have considered one macro base station which is capable to operate in 2 frequencies, frequency 1 and frequency 2, and also there are 4 neighboring micro stations which also have a possibility to work in 2 different frequencies. There are 2 types of users. The gray users are voice users, so let's say low traffic users, and the black users are MBB, so we can treat them as high traffic users. And the question is how to allocate these users to these base stations. And of course, normally it will be done that the strongest signal will be the key criteria, but now we will have these policies. If we have a different look on the same scenario, it is that we have the macro base station which can operate in cell 1 and cell 2, so on these 2 frequencies we have a set of small cells, and then we have a rig that is capable and that can control the functioning of the entire network, and this functioning is within our traffic steering, or we also use interchangeably the name cell association xApps. So we can change between different frequencies. We can change between, if these are active, of course, we can change between the macro and small cells. Okay, so how it will look? So normally, if we have the situation as in this slide, we have this 4 UEs. So normally, based on the distance, in fact, so the received signal strength will associate users in that way. But if we apply some policies after application and running of the xApp, this association will be changed. So we can force that all the heavy traffic users will be served by small cells, and low traffic users, for example, these voice users, will be served by macro base station. How we could implement it in terms of policy. So as I mentioned previously, this xApp should have some input parameters. So this will be the received power. For example, it will be cell class, so meaning if this is what type of cell we have in the network, if this is small cell, macro cell, what kind of cells, what is the traffic class, and also what will be the association policy. As the outcome, we will have the association table, so the instructions how to associate these type of users to within this particular network. And these policies, as I mentioned, these policies can be in the simplified way, as we can see on the right side. Of course, this can be much more complicated, but we could have on this figure, we have 3 exemplary policies. So default one, offload and separate. Default, simply we can see that voice, here we see that the relation of how voice and MBB users should be served or treated by the Pico base station and micro base station. So in the default, there are no preferences. There are no preferences, so both voice and MBB users can be treated in the same way. But if the operator applied offload policy, then it is written there that voice users shall be avoided in the context of Pico base station, and MBB are preferred. And then there's a separate, which I mean intuitively means that all the MBB users shall be served only by the Pico base station, and it is written here on this policy. So here we have these words: avoid, prefer, forbid, and shall. And okay, what does it mean at the end? It can be implemented in such a way that different vendors, different operators could apply different, for example, weighting coefficients to this particular word. So operator 1 will say, okay, default means 0, prefer means 10, avoid -10, and shall is, let's say, 1000 and -1000. The other may work in different way. At the end, within the xApp, these weights will be treated, I mean, accordingly to accordingly. So if this is separately applied, then much more stringy requirements will be put on this separation of these of the users. Okay, so in the localized scenario, before we go into the true implementation and SD-RAN, as I said, we did some initial tests to see if the traffic steering algorithm works at the end as we expect. So here you can see the coverage map of the considered scenario. So on the left side, we have the situation for the voice UEs. On the right side, we have this MBB UEs. And here is the very simple sketch of the coverage, potential coverage map. So the color means the area associated to the specific base station. So here this light green means that if the user is here in this area, it will be automatically associated with this particular base station. So in this case, when the policy default is applied, both voice and MBB UEs, these will be associated, as we can see here on this map. So it's mainly based on the distance. But then the concept is that when we apply offloading, then offloading means that we try to offload the heavy traffic to the micro base stations. So it means that voice UEs are expected to be served by the macro base stations. So the effective coverage area is, as you can see on the left part, and effective coverage for MBB users is as on the right side on this slide. So what we have here is that the coverage area for the MBB has increased in the context of micro base station. So the effective coverage area is greater than when we compare it with the default one. This is of course expected situations. How we have tested the performance? The performance was tested when we compare the cumulative density function with some predefined threshold. So just briefly, this traffic steering was implemented in such a way that in a simple words, that when the mobile network operator select, let's say, offload or separate policy, we have added additional factor, additional parameter into the path loss, very similarly as the cell range extension is done in nowadays wireless networks. So by adding this offset, we are able to effectively impact on the final association. So here we see on the left side, we see the top view of the network. So the red dot is the macro base station. You have this this is macro, and this blue are the micro base stations. We have the values here is the achieved throughput by this UEs. These dots are some UEs deployed here randomly. Black dots means voice users, and pink means MBB users, and these dotted lines, they represent associations. So if the default policy is applied, as we have discussed previously, the distance is the crucial factor that decides on the association. And here when we observe this cumulative density function, so it is the percentage that, okay, if we look on this number, so it means that 60% of users have a throughput above this value. So this is the meaning of this cumulative distributed function. So here we have the CDF of the bitrate, and we can see some curves showing the performance. This vertical lines, these represent the thresholds. So in order to serve the voice user correctly, the rate has to be above this line. So we can see that for all these voice users, this requirement is fulfilled. For the MBB users, the situation is not that good. So it is of course observed in the outage probability. So by outage we mean the situation that the user is not associated, base station does not have enough resources to serve this particular UEs. So the goal is to minimize the outage by keeping the rate as needed. So let's compare what will happen if we apply this offload policy. Okay, so we see some improvements. As you can see here, there are different associations. So we can see that these pink elements, these are associated with the micro base station as expected. What we observe is some reduction, some drop off with the rate observed by the voice user, but everything is still fine because we are above the threshold, and we observe significant gain, meaning the curve is shifted right for the MBB users, which is reflected also in the number of outage users. So we can see that this simple policy, as I said, intentionally it is simple to visualize the concept. This simple policy can lead to improvement in terms of average rate and also minimization of the outage. So it is expected. Of course, this part will be described in detail in a while, but let me just briefly present the situation where we have three xApps working together in our localized scenario. So the scenario is as previous, so we have these two different frequencies possible. We have these 5 base stations around. Each of these micro base stations can also use different different frequencies, and we have these users deployed randomly. So we may have different levels of traffic steering between two cells and within one run. So the issue is that our cell association xApp, we can switch between the different cells, but then we could select different frequencies. This is this violet one. And the third level, which is not mentioned here as a bullet because it is within one particular base station, is that we could also modify how the resources are associated, how the resources are managed for the specific user. So we have this three level of scale. So of course frequency selection will not be that frequent. The cell association may be much more frequent, but of course it will be not that frequent as radio resource management. So we have these three levels of three time scales. So let's say we can trade a short one, a long one, and the medium one is the traffic steering. Of course, this time scale they depends on the priorities and expectation of the mobile network operator. So how it operates for the, we know that, we see that figure previously. So we have macro cells and small cell. So the first step will be to select the frequency, then how to associate them, as we saw previously, so based on some policies, and then how to allocate bandwidth within the cell among the base stations. So then this resource allocation xApp will finally decide how many or suggest how many resource blocks, for example, could be associated to this particular type of traffic. So small cell will associate more bandwidth towards the UEs of MBB type. And of course, we applied similar approaches to all of these xApps. So as you remember, we have these APIs. I will not go into much details, just to show. If you are interested, you can stop this video and analyze in detail these APIs. So this is the API for the first one with the policy examples, as we have discussed previously. And we have the same for resource allocation function. Here, of course, the association policy is important, UE class as well, and as a result, we will have association allocation table, with some policies again specified in similar way as previously. So how specific type of traffic should be treated in terms of radio resource management. And finally, the spectrum management function, again, we should of course as the input has the possible frequency bands and spectrum policy, and as the output will have association of users to some specific frequency bands. And again, we can have the policy, tree performance, how we can call them, based on the mobile network operator expectations. And some simulation results. So here we see the same situation as previously. So we have policy association and policy association default for the for different xApps. So we have default and default in both cases. But then if we apply offload in first case and default in the second, we observe some curves. So this is for the traffic steering. And then when we upload the reservation policy with the default one, we have a completely different performance in terms, I mean, if we concentrate on the networks. So by different mixture of different policies, we may achieve different results. So this is important to remember this. So offload and some other policy, then we change traffic steering to default, and we select some other policy, we observe some other performance, which is obvious and expected. So the point is that we can learn everything. And we could have some changes in time domain. So here is the situation. Here's the situation where we observe the change. For some reasons, there are change of 10% of voice UEs to MBB UEs. So we observe here outage as a function of time. Here we observe the bit rate observed by the users. So here on this time slot, there are 10% of UEs which are turned into the MBB UEs, and we observe, operator observes some drop in terms of outage. So it can decide to apply offload policy, and as a result of offload policy, we observe some improvement in terms of outage. We have some decrease of bitrate, but we are still above the average required value. So by applying this policy, we can improve the network performance significantly. And of course, the role of the intelligence hidden inside the rig and inside the xApps is to select the policy based on some observation, previous experiments, to select these policies in the best way. Now let's go towards the integration with microNOS. Based on all this implementation, all these parts, what we did is that we tried to implement in this open source platform, this SD-RAN with Open Network Foundation. The concept was to make it suitable for heterogeneous scenarios, to have per user association decision. It takes all the important parameters available in 5G networks like this RSRP and 5QIs, and the goal was to optimize user throughput and cell outage. As I said, we concentrate on the integration with the microNOS, and this is open source, and that's why we show it in this tutorial, because it can be easily downloaded, and you are encouraged to go and also download this particular traffic steering, which is also released in form of an open source. I will not go into much detail of the microNOS, which is a bit behind of this tutorial, but here what's important to add is that here what you can see in the middle of the slide is the version 1.2 of the SD-RAN framework. What is important to say, there are different ways how to implement the xApps. Our part, we use Golang SDK. There are 3 xApps already that resides there. Then this remains the traffic steering xApps, and we have implemented this, and then we communicate with ONOS topology, with ONOS E2T and A1T to get, and through E2T we get information from and about the connected base stations, and through the A1 interface we connect to it. We get information about the policy. So everything is integrated within this framework. So as you can see, our JSON policy, as we have discussed previously, will be delivered through A1 interface to our traffic steering xApps. This will be utilized and used by the software, and some decisions will be made and enforced through the E2 interface. Of course, as will be shown in the fourth part of the tutorial, there is a portal where we can visualize the effects of this particular traffic steering xApp. So this is the summary of or let's say high level view. So as I said, this RSRP and 5QIs, these go through E2 interface to the specific MHO model, which consists now this traffic steering model. We get information about the topology as well, and through A1 we get information about the policies. And on the right side you have the necessary versions of modules, I mean, to run this traffic steering xApps. And of course at the end, okay, so I forget about this slide, so you have also some detailed description of all the input parameters, what is needed, and of course for those who will go into implementation, this traffic steering is also described in forms of Helm charts, so it's well designed for training as well. So you are encouraged to analyze it and simply learn how it could be implemented. And finally, some policy management part is that there is a question how to upload the new policy, how to delete it, how to check the policy, and in this implementation that you can learn and you can train. We apply the REST API approach, so through some REST client. We can go through the A1 interface, accessing the endpoint NYT, and then we can go to traffic steering xApps. As you can see, if we have this, let's say, this dedicated IP address, we can use simply this put or get methods exactly specifying what should be delivered. So this policy end of that kind, where we see that for this cell ID policies. We could have prefer, the preference level prefer. This policy could be delivered to the traffic steering xApp. Then we can of course check what is the current policy through applying this get method in the same way as the REST API is working, and also we can delete it if needed. Okay, so this is the everything what I wanted to say in this part 3 of this tutorial. So what we said is the presentation of the use cases, some historical view and current view on the use cases. There are 19 of them, and the reason why we have selected this traffic steering, and which acts here as a training part for the use case. We have discussed also different deployments very briefly, but providing some insights what is happening in terms of practical deployments. And then the crucial part of this third part of this tutorial, this is this traffic steering use case presentation, showing what it should do, what is the expected performance, and what should be achieved when we implement in the real network. At the end, we have this advanced use case with 3 xApps included, and we end up with integration with SDRAN. So now let's move to the fourth part. I would like to thank you for listening and for watching this tutorial. It was a great pleasure to present this part, and I warmly introduce and invite you to the fourth part, where you'll be able to train the implementation of the traffic steering xApps simply on your own computers. Thank you very much, and goodbye.